Hello guys, this is CodeNCode and this is third lecture of this basic algorithm series, and till now we have been studying binary search. So previous lecture we have seen what is the core idea of binary search and what are the functions and monotonic property of the functions. So you can apply binary search on any function which is monotonic. So what we have studied till now, we are going to implement this in this problem, Monk's encounter with polynomial. So this is basically a practice problem for us to implement whatever we have studied till now. So the problem is fairly easy. We are given a polynomial which is quadratic and the function is ax square plus bx plus c. There are t test cases. In each test case you will be given a, b and c, that is coefficient for polynomial, and also an integer k, and you have to find smallest x such that f of x, if I call this as f of x is equals to ax square plus bx plus c. So find smallest x such that f of x is greater than or equals to k. This is the task. If you see, there are t test cases and t can be as large as 10 to the power 5. So there are 10 to the power 5 test cases. In worst case, a, b and c can be up to 10 to the power 5 and all of them are positive. Now k can be itself 10 to the power 10. Now these are some of the example. I'll be explaining these example in detail in the same lecture. So this is the function we have previously proven. We have already proven that this function is actually strictly increasing function, and since this is a strictly increasing function, hence we can apply binary search here. Now before that, let me explain some of the important concepts of the remaining concept of binary search, how we proceed with it. So I have plotted a graph for the function tan log x. The graph looks like this, and log x is actually a strictly increasing function. And suppose we have to find smallest x such that this f of x is greater than or equals to 10. So k here is 10, right? Now the given range for us is 5 to 20. So in the range 5 to 20, find the smallest x such that f of x is greater than or equals to 10, right? So what we would do, since we know that this function is actually a monotonic function, since log x is actually strictly increasing function, hence f of x is also strictly increasing function, which is a monotonic function. So we can apply binary search here. So what we do, we calculate mid, which is 25 divided by 2, and we try to find the solution. Now see, in each iteration we will calculate mid. The purpose of mid is that mid is either your solution, or mid divides the whole active range, which is 5 to 20, into two halves. First a valid range, second an invalid range. So first we'll check whether the mid is solution or not. If this is solution, we'll simply return this. Otherwise we will reduce the whole range into half. Now what is the condition that mid will be our solution? Now see, if mid is our solution, then f of mid should be greater than or equals to k, of course, right? Since we need to find smallest x such that f of x is greater than or equals to k, which is 10 in this case. So mid to be solution, f of mid should be greater than or equals to 10, right? And also, since there are many elements, since this f of x is actually strictly increasing, so if say x naught is actually the smallest x such that f of x is greater than or equals to k, then any number above x, that is above x naught plus 1, x naught plus 2, x naught plus 3 till infinity, all of those number will be greater than or equals to k as well. So checking only that okay, f of mid is greater than or equals to k, then it is solution, that would be wrong, because see, 10 is the solution actually, because f of 10 is greater than or equals to 10, greater than or equals to k is 10 here. So 10 is the solution. So see, f of 10 is greater than or equals to k, f of 11 will also be greater than or equals to k, and in fact any number greater than 10 will be having f of x greater than or equals to k. So checking only the condition, okay, if checking only the condition that f of mid is greater than or equals to k is not sufficient. For for mid to be solution, mid to be the smallest number such that f of mid is greater than or equals to k, f of mid minus 1 should be smaller than k. So these two conditions we need to check. These two conditions are the one which made sure that mid is the solution. So for mid to be the solution, the condition is f of mid should be greater than or equals to k, and f of mid minus 1 should be strictly smaller than k. If f of mid minus 1 is strictly smaller than k, that means all of the numbers below that are also smaller than k, which means mid is the only number from 0 to mid which is greater than or equals to k, which means mid is the first number which makes f of mid greater than or equals to k. So mid to be solution, there are two conditions. First, f of mid should be greater than or equals to k, and f of mid minus 1 should be strictly smaller than k. The same condition we will check for this problem as well. Since we want since this is also a strictly increasing function, so we can apply the same approach that we are applying here. So for mid to be solution, if I show you the code, let me go for full screen mode so that so that this is more visible. Just a second. Okay, 120%. Yep, and full screen. So this f of x is actually this is a function. LLI is long int. I have defined here long int. So wherever you see LLI, that means long int, which is 64-bit integer. So f of x will return long int, which is nothing but ax square plus bx plus c, right? So you see I am evaluating the function. This is L, this is, just a second, make it more visible. So you see what are the rest I'll be explaining in a moment. First, see, we calculated mid, and then I evaluated function f on mid as well as mid minus 1. So mid will be my solution if and only if f of mid is greater than or equals to k and f of mid minus 1 is strictly smaller than k. That is the condition where when mid will be my solution. So you see, we are able to see whether mid is our solution or not. What happens when mid is not the solution? Then we'll go to reduce the ranges. Either we'll update lower pointer or we'll update the higher pointer. Either we'll update low or we'll update high. How we decide that? That is another question. What are the conditions which makes you abandon either the upper half or the lower half? Now writing condition for lower half to be abandoned is the condition actually is easy for both of them, but let's go to see what is the condition when lower half will be discarded. Because either your mid is your solution or your mid divides the whole active range in two parts, one of which potentially contains your solution and another one does not contain your solution. So if this range doesn't contain my solution, then what is the point of having the active range from here to here? I can simply reduce my active range and remove all of these elements from my active range, so I can set my active range from mid plus 1 to right. This is low, left and right, and here I have used low and high, so these are the same things. Now we know that how to find whether the mid is solution or not. Let's see how we can after that you know that okay, mid is my solution, you simply return it. Otherwise we are going to reduce the range. So to reduce the range, we have to see, just a second, we have to see that whether we have to discard this range or we have to discard the upper half. Either the lower half will be discarded or the upper half will be discarded. So let's write down the condition when the lower half will be discarded. If the mid is not the solution and f of mid is smaller than f of mid is smaller than k, we are finding smallest x such that f of x is greater than or equals to k, right? So if mid is not the solution and f of mid is smaller than, if f of mid which is x here, f of mid is actually smaller than k, in that case what happens, we will discard the lower half. Why? Since f of mid is smaller than k and the graph is strictly increasing, the function is strictly increasing, what will happen is that any x you choose in the range from low to mid, every single for every single x in the range L to mid, f of x will be smaller than x, and hence none of the number in that range can be the solution. That is why we are going to discard the lower half, and we will set the lower pointer to be mid plus 1. That is because the range, now the active range will be this, the upper half. That is why we'll update the lower pointer, otherwise we'll update the upper pointer to be mid minus 1. So let's see the full code. So here long it again. There are t test cases. In each test case we are reading a, b, c and k, and again a, b, c and k are declared here globally. So after reading that, we are calling binary search and printing the result in next line. Now in the binary search function, we are using this function f of x as subroutine, which will do nothing but evaluate the polynomial on x. So it would return ax square plus bx plus c. That's all. Now see, if c itself is greater than k, then x is equals to 0 is the minimum. So that's why we are returning 0. Otherwise we will be searching for result in L is equals to 1 to ceil of square root of k. Now this is your assignment. Try to prove that high, that is the upper bound of answer, cannot extend cannot go beyond a ceil of square root of k. Ceil means if the result is 3.7, it would convert it to upper integer, which is 8, the nearest integer. So nearest integer which is on the right side of that point on the x-axis. So this is your assignment. Prove that the result won't pass for the polynomial ax square plus bx plus c, the minimum x, such that ax square plus bx plus c is going to be greater than equals to k, will not go beyond ceil of square root of k. So the upper bound is ceil of square root of k. This is your assignment. Prove it, and you can show the proof, or you can write down the proof of yours on discuss.codechef.com, the article that I've created for this course. Let's continue. So L, low and high are these number, and of course I have already explained this. So if you run the code, let's just run it again to see everything goes perfectly fine. Oh sorry, I think I haven't connected it to internet. Sorry, it doesn't actually matter because I'll be giving the link to the of the solution in the description of the video, so you can test. Okay, the code is exactly the same and passing as well. So this was all for this lecture. If you have any doubt or query, of course do ask, and ask in the article that I've created for this course on the discuss.codechef.com. Do not ask in the comment section of YouTube video. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.